All right. Morning, everyone. Thank you for joining us. Monday class. A lot of fresh faces. How was the weekend? Anything? A lot of work. No fun. Just work, no play. Well, that sounds like my weekends, right? So that's why we're here. Pretty excited. Okay. We had a game, right? And I uploaded a special assignment on Canvas. So remember to fill in to get that extra 2 points. And Team Zebra, just upload your team member so I know who you are. You don't have to do anything. You got to, you guys get like 10 points for that competition. So again, kudos. I think anything else is just about homework number 2. It's due this Thursday. I haven't finished grading number 1 yet. Apologize, I'm working on it. Imagine I have 3 proposals and 6 grad students that I've talked to today. And so with you guys, it's like, what, 70 homeworks? So it took me a little bit while, but I think we're okay. I'm more concerned about the second homework. Like I said, the 4 sets of homework, I will be grading myself. So that's close, intimate interactions between you and me. And there's our certain level of a client and attorney privilege thing. I see what you do and you feel like, if you're doing a good job or not. So these first 4 sets of homework are very important. Make sure you submit and have good qualities, right? And I'm not saying the rest of them are not, but the rest will be graded by the graders, right? So hopefully you do a good job in the first 4 sets of homework. My intention is that if you can do 4 good homeworks, I think you guys should be ready for the exams, okay? All right, attendance. I feel like we have less and less attendance as the courses getting in. Thursday lectures especially, it's just heavy and probably want to take a quick break. Don't want to see me for continuously, 3 days in a row or whatever. So to help us to boost up the attendance, we're starting doing the sign-in sheet today. All right. So if anybody have a piece of scrap paper can help and put your name down and just circulate around. So today I'll start collecting attendance. Okay. So you can tell your friends that Bob actually takes seriously about this attendance business. So tell them to do attend my class, okay? I have online option as well. I only have 1 or 2 students who suspect to have COVID, but as Omicron cases dropping down, I see that excuse get used less and less. So if you do have some problem, let me know beforehand, so I will know that you'll be attending online, okay? Recording. I uploaded recording to YouTube channel. I usually label them by date and time, so you know what to look for. If you are a little bit ahead of the game, you want to learn more, feel free, welcome. All right, just scroll up and learn something, but be mindful that what we taught last semester are a little bit different from what we're going to teach this semester. Subtle differences, right, in terms of examples and everything. So that means you do have to attend this lecture, okay? The other lecture help you understand and maybe enhance your memory, but that will not replace what we're teaching this semester, okay? All right, last thing but not least, we are almost like what, 1/3, not yet, but close to that time in the course. So whoever want to drop has dropped already. Whoever haven't, you're here. I'm very happy with you. So let's talk about commitment. How many of you guys have bought the ACI code 319? Okay. If you haven't, do it. do it, okay? Starting from second homework on, it's gonna be harder and harder, okay? First exam, you need the code, so do get one, okay? Do get one. Now, how many guys has bought the textbook so far? Few, okay. Again, strongly recommended. Strongly recommended. Get the soft cover, get the electronic version of it, whichever cheapest you can go for. You don't have to buy the expensive one. Older versions are fine, right? Edition 9s, I think is out, but you can buy 7th or even before that, okay? Minor differences, doesn't matter. I hope the textbook can help you to learn, which I'll show you how we're gonna use the textbook a little bit today, okay? All right, so that's that for everything. Any questions for me? Any big concerns and everything? Okay, so far lecture's been going well, but I have a travel, I'm old, so I'll be traveling a little bit before spring break. My plan right now is give you a little bit time off, right? We can do some online. So connect the spring recess to the spring break. Is that what you guys thinking already? Smart, I know that, right? I'm thinking about the same thing. So most likely we will do an online session in between, so you guys have more freedom, but online session meaning still attending lectures, right? I know sometimes you watch YouTube or Netflix or listen to my lectures, right? Recording will come after, but that's fine, okay? But at least don't let me hear the background noise about it, okay? All right, so that's the plan about spring break and spring recess. And let's get back to it. What we learned. Oh, surprise, right? Don't be surprised, right? Beginning lecture every time. What we learned. This is reinforced concrete design. Two things. One is reinforcement, one is concrete. Now, concrete is good for what? Compression. Come on, you eat breakfast? Did you? What concrete is good for? What concrete is good for? There you go. What steel is good for? There you go. You need a tension, compression, combine them. You get the best out of the two words, and you have reinforced concrete design now. Okay. How do we analyze the section strengths in terms of moment? We start from where? Bob, we start from energy drinks. Start from coffee. Sure, that's one word to start. Where we start? From equilibrium. Equilibrium, two things, tension and compression. Where do we start first? Tension or compression? Tension. How do we get tension? Area of the steel and the yield strength of the steel. What is the yield strength for a grade 60 steel? 60 KSI. So I have 4 number 9 bars in the section. How much of tension force I have? 240 kips, right? To balance that, I need to use Whitney stress block, right? What is Whitney stress block? 0.85 F prime C, A and B. What is A? Effective compressive size, right? Length, right? That is equal to what? Beta 1 C. What is beta 1 for F prime C equal to 4 KSI? 0.85. There you go, right? And B is the width of it. Now, 240 is the tension. I can calculate my A, which is effective compressive zone. Afterwards, I need to find my moment, right? My moment is nominal moment capacity, Mn, equal to tension multiply the distance. And the distance between the centroid of the compression and the centroid of tension. And that distance is, folks, ds minus A over 2. There you go, right? And after I get a moment, I need to determine phi. What is phi? Strength reduction factor. And phi is a function of epsilon s or epsilon t. T, right? Not S and T, right? It's T only, right? Technology, right? S and T, right? T, right? Epsilon T. How do we calculate epsilon T? Use that triangle, right? Strain diagram, right? That is d what? Minus C over C, d what? ds or dt? dt, right? dt minus C over C multiply epsilon Cu. What is epsilon Cu? A crushing strength of concrete. What is that value? 0.003. You got it. So that is how you calculate moment capacity for a singly reinforced section. What does singly mean? Tension reinforcement only. Now, what afterwards? Afterwards, had a game. Everybody's kumbaya. We went home. Sure, that's what we did. Coming back, we learned from AA reinforced section. What is the difference between AA and singly reinforced section? Is AA, we added what? Compressive reinforcement, is that right? So question, problem number 3, maybe exam number 1. These are the advantages for double reinforced section compared to single reinforced section. A, increasing ductility. B, increasing ductility. C, increasing ductility. D, increasing ductility. Which one? All of them, right? You're right. Increasing ductility. Okay, all right. So that is the key of doubly reinforced section. So we increase the strain in the tensile bars to increase the ductility of the section. So that is the difference. Now, apart from that, the equation for doubly reinforced section changes, isn't it? Right? What changes? Two things: equilibrium and moment capacity. Now, in addition to the compression force from the concrete, what do we have now? Compression force from the steel, isn't it? How do you calculate the compressive force for the steel? ES, which is modulus Young's modulus or modular elasticity for steel, multiply epsilon S, which is the strain in the steel. Did I forget something? Epsilon S what? Prime. Why prime? Prime meaning compressive, right? How do I calculate epsilon prime? You use the depth of the compressive reinforcement, which is ds prime. What is the ds prime? Usually equal to concrete cover, isn't it? Because it's on top. What is the typical concrete cover you see most so far? 2.5 inches. Wonderful. One additional note, please write them down where we add it. For a single layer reinforcement, okay, single layer reinforcement, that is in the tension side. The concrete cover is usually 2.5 inch. For multi-layer reinforcement, without knowing anything, the concrete cover is usually 3.5 inch. Note them down, okay? Note them down. We need it for analysis and also for design later, okay? Note them down. All right, so let's come back to the compression force of the reinforcement. So ES, epsilon S prime, great. That gives you the compressive force, right? So total compression now equal to CC plus CS. So should I just put 0.85 prime C, AB plus AS prime, epsilon AS prime, ES, epsilon S prime? Can I do that? Of course not. I missed one thing. What did I miss? There is a subtraction, right? And that equals to minus 0.85 F prime C. Where is that minus 0.85 prime C coming from? Because I put compressive reinforcement in the top, so I occupy some of the compressive area for concrete originally, right? So I had to take that out to consider that effect, subtraction, okay? So that is the difference. That is the difference. So once you have that, you just have to sum the moment, right? For the moment capacity. So we don't have to go over that long equation. I'm short on memory, okay? You can go back, refresh that. So that's what we learned, okay? That's what we learned. So we learned singular reinforced, we learned double reinforced. And what happened? What happened, Bob? We had to put the bars together, right? We had to put the parts together. So what is the thing that we talked about last lecture about detail, about the spacing? End of it. It's staring right there in your face. And let me just put it amplifying here, right? What is what we learned here? What is called this thing called? Read it out, please. B minimum. What does B minimum mean? Minimum width of the section that allow us to put so many bars in it. So that means if I tell you I am going to put so many bars into the section, you need to give me a size or dimension of the section, width of it, that can accommodate so many number of bars, right? So how do we write that? How do we get it? We do that by calculating the detailing, right? So we know that the concrete cover is 1.5 inch. So we go from the left side extreme, right? Incrementally increase, right? The spacing all the way to the corner bars and accommodating the spacing, clear spacing 1 inch between the bars, right? And then add them up and including the stirrup size, give you the B minimum, okay? So that's everything you need to know about design, okay? But we're not finished yet. This is only one row of bar. Today, we're going to look at 2 rows of bars, okay? 2 rows of bars. So bear with me, let's start the game. So now, look. We have talked about 1 row of bars. It's wonderful, right? What if I have a section look like this, perfect square at the bottom, and I have bars here, say 3 number 9 bars, 1, 2, 3, okay? And I have 2 number 8 bars. Remember, it's on the side of it, don't put in the middle of it. Why is that? Because we need to tie them up to the stirrups next to it, right? So number 9 at the bottom, number 8 on the top. This is what we have. And then to put the stirrups here, I need to get this tangential line right up here. And this is actually a little bit offset, but let me do this. And here I tangentially intersect, then come up here and do this. My drawing is horrible, but you can get the general idea. Okay, get a general idea. So this is the stirrups on the outside of it. Okay, on the outside of it. Let's say the stirrups is number 3. Now, what is the diameter for number 3 bars? 3/8, right? So 0.375 inch. Great. So now I have one layer of reinforcement right here. Okay. And I have a second layer reinforcement at the bottom here. And if I say that I have a distance between the layers, that is clear spacing has to be 1 inch. You see this a lot, okay? 1 inch is somewhere I use a lot. Clear space of 1 inch, okay? The question is, what is the center of the, what is the centroid of the group of the bars? What is the centroid of the group of bars? What is it? How do we calculate that? How do we calculate that? There is an equation, remember? Long time ago, galaxy far, far away. There's a Anakin Skywalker. Oh, no, sorry, wrong scene, right? What is it? What is that equation? What is that equation? Say if this is, let me give you a hint. So this is A1, all right? And the distance between the centroid of the first row to the bottom line here, let's just say this is Y1, okay? And I say I have a second row, let's call it A2. The distance between the centroid second row to the bottom here, Y2, right? What is that equation? So what is the distance between the centroid of the group bars to the bottom surface here? Let's call it Y bar. So Y bar equal to what? Come on, Y bar equal to what? Somebody? A1, keep going. Y1 plus A2, Y2, there you go. Divided by what? A1 plus A2, there you go. Okay. That's very simple, right? Okay. Now, what is area for single number 9 bars? Cross-section area. 1 inch squared. What is the cross-section area for number 8 bars? What is it? 0.79 inch squared, close. Okay, 0.79 inch squared. Wonderful. All right. So now you have this information, right? And let me just say that assume, this is assumed, okay? Assume I have a distance, okay? Distance between the centroid of the second row of bars, and that is Y2. Let's say that Y2 equal to 2.5 inch, okay? And Y1 naturally equal to what? 2.5 inch plus half diameter of the number 9 bar, which is what? Which is what? What is the size of number 9 bar? 9/8, right? And then multiply half, and plus another clear spacing 1 inch, and plus another half of diameter of the number 8 bar. What is the half diameter of the number 8 bars? What is diameter of number 8 bars? Come on. 1 inch, right? Divided by 2, what? 0.5. Okay. All right. Now, you have all the information you need, right? So pull out your calculator, help me out here. Let's see what you get for Y bar. Can you do that? Can you do that? You have the equation, you have the parameters. Yes, you're right. I'm not let you sit there and listen to me yabba yabba on Monday morning, right? Pull out your calculator, use your brain, let's see what you get. Okay, and don't look at my old notes. My old notes, I have so different numbers here. I don't even remember what I have there anymore. Okay, new problem today. Let's try it. Let's try it. Okay, 2 number 8 bars, 0.79 inch squared multiplied by 2, right? That's roughly 1.58 inch squared, right? And distance is what? 2.5 plus 9/8 divided by half, right? Something like that. So get this number. Okay, get this number, right? Okay. Okay, and let me help you out, right? Let me do this first. While you're working on a calculator, let me do my hand, okay? Let me do by hand, okay? So this is 3, 4. So this is what? 9/16. So 4, 9/16. Okay, so roughly equal to 4, 8/16 plus 1/16. So this is what? Half 4.5 plus 1/16. 1/16 is 0. 6, something like that. So 4.56 round up inch. No calculator. You guys say? You guys say somewhere like that. Okay, to be precise, something like that. But anyway, right? So that's Y1. Okay. You do your calculator. Okay. Check me by hand. Okay. Y1 equal to 4.56 inch square. That's 2 number 8 bar 1.58 inch square, and this is inch plus 2.5 inch multiplied by 3. Sorry. Inch squared divided by 4.58 inch squared. Okay, so y bar should equal to, let me do this way. So this is this. So that's 4.5 multiplied 1.6 approximately, plus this is 7.5 bottom here, 4.6. So this is Bob's approximation, crude calculation. Okay, so this is what? This is 4.5 multiplied 2 multiplied 0.8. So 9.8, 7.2, 7.2, 7.5, 7, 14.7, 4.6, roughly equal to 114.7, 4.7. So let's do roughly 15, 15. So roughly 1/3 of 3 inch. Off by 20%. What do you have? What do you guys got? 3.21. Do I get a second?
Yeah.
Okay, so my hand calculation is not too bad, isn't it? All right, so you got 3.21 inch. What does it mean? What does it mean? What does it mean? Anybody? What does it mean? Well, it means that the centroid of the group of bars to the bottom line here is 3.21 inch. Is that right? 3.21 inch. Now, if I have a single layer, my concrete cover is 2.5. Now, if I have 2 layers now, right, my cover becomes 3.21 inch. So that's where I said, if you have 1 layer bars, you say the concrete cover or DT equal to H minus 2.5 inch for 1 layer. Okay, and if you have multiple layer bars, you say approximate H minus 3.5 inch. Remember this? I said note it down. That's where it's coming from. Okay. Okay. So this you can start your calculation without actually doing the details. All right, but this is checking after the fact. Okay. So that is how we check for multiple layer bars. Right now, question for you is: I have now a number 9 bars, right? And 3 of them. And I calculate the cover, concrete cover 1.5 on the side, 1 inch clear cover between the bars, right? And I have a minimum beam width about 9.25 inch, right? And as I say B minimum is 10 inches, right? Do you want to do this every time? Let's see who want to do this. Raise your hands up. Just me? Oh boy, am I the lucky one? Nobody want to do it? Of course, nobody want to do it. Why? It's too much. So, is there a shortcut? Yes, there is a shortcut. How many guys bought the textbook again? Okay, if you bought a textbook, it's a PDF or hard copy. Open it up and have the hard copy. I have the software copy, and go to table A5. Go to table A5. That is on your appendix of your textbook. Okay, and what is the title for that? Read out for me, please. Minimum beam width for multiple, yes?
Oh, I'm sorry, I had a question about what you.
Yeah, let's solve your question first, yeah.
So in the notes of when we calculated DS in the past, it looks the same as when we calculate DT.
Yeah, that is only one, we have 1 layer of bars.
Okay, so DS
Exactly. Yeah. Okay, good, no problem. Yeah, so let's get back to this and see, this is table A5 and it's called minimum beam width for multiple US bar per layer. For multiple US bar per layer. So that means in our situation, I can choose my beam width from this table. Okay, how do I choose that? What kind of situation I was in? How many bars in the one layer? 3, number 9 bars. So I go number 9, which is right here. Can you see that? Can you read out for me? Number 9 bars. How many bars I have there? 3 bars, right? What is the minimum beam width? 10 inch. Okay. This is not precise, right? It's just a round number. So you can use this table for the design. Okay. But in exam, you can not only use this one. Okay. In exam, you have to do both ways. Okay. Calculate the exact number and come back, check this table A5 to see you have the similar number or not. Okay. But there is a shortcut. There's a shortcut. Okay. All right. I think with this, we're done with this spacing details. Are we okay with this? Are we okay with this?
Yeah, to like different number of bars and the different layers, affect how close our value is to that.
Well, think of it, right? You have 2 layer of bars in this scenario, right? If I say these 2 layers, right? I have 2 layers. Which layer do you think will be the controlling layer? Why?
It's yields first.
And also why? It has more bars as well, right? It needs to accommodate more bars, right? So very good question. In a scenario that I have multiple layer bar, pick the layer that have most number of bars. Use that layer to dictate your minimum beam width. Okay, clear? Good. All right. Okay. So are we okay with this now? Are we happy with this? Any question about it? Any question about it? Anything? No? Okay. We'll come back to talk about it. Okay. There are 2 questions remain, actually. 2 questions remain. Okay. I did not talk about it yet, but 2 questions remain. What are the 2 questions? First of all, what is the concrete cover I say here? 1.5 inch on the side, isn't it? 1.5. Why? Have you asked me? Why 1.5 inch? I don't know, Bob. You said 1.5 inch. Well, I said a lot of things, right? I told my wife tomorrow is Valentine's Day, right? Yeah, of course, she didn't believe that. Anyway, right? I said a lot of things, right? So I found this 1.5 inch from the ACI code. From ACI code, okay? There are actually 2 tables tell you which concrete cover you need to use, which I did not say anything yet. Okay, I'll tell you next lecture, okay? But not today. So that's one question we need to address. Second question, what did I say about a clear cover between bars? 1 inch, is that right? 1 inch. Did you ask me why? No, you didn't. You trust me blindly, right? You trust me blindly because I look okay, you know, look like a professor, pretty nerdy, right? He knows what he's talking about, sure. But why? Because we need to have a aggregates, right, to flow through it. Because we have to have certain bars to insert between bars. All these are actually documented and listed in ECI specifically, which I will provide next lecture. Okay, so these are 2 questions. And you ask, but why can't you give me right now? Those actually parameters needed also for bonding, for splicing and those details, okay? I'll talk about that next lecture, okay? All right, so at this point, we're done with beam width calculation. 2 things you learn, right? What are the beam width calculation? One is we know how deep the bars are, right? In relative to the bottom surface of the concrete. We know how to do that, right? Multiple bars do the calculation. We now also know how much beam width you need to have accommodate so many bars in it. So now we are truly ready for design. We're truly ready for design. Okay. All right. So you may ask me, Bob, we did design already, right? Last time we did a competition, right? We give you you give me a section, tell me what kind of bars I need to use, and you ask me how to calculate it, right? Sure, you did, but that was not a formal process. Today, we're going to talk about the formal process of doing design. Okay. So new lecture, lecture 6. Let's talk about design, okay? Design. Okay. All right, so lecture 6, design of be careful here, okay? First thing, design for a singly reinforced section. Okay, and this is design part number 1 or part 1. Okay, and let's us to take something very easy. This is only unknown reinforcement, but known section size. Okay, that means I'll tell you the section size. For example, I have a section like this, and I give you a width of it. So let's say B equal to 12 inch. And then I have a height of it, which H equal to 24 inch. Okay, and I'll ask you, what is my reinforcement needed? Okay, what is my reinforcement? This is so-called design for unknown reinforcement. Okay, so how do you start? Or rather, yeah, is this question complete? Can you start with this information only? Can you just start design right now? Can you start right now? It's like you're a contractor, you go out there on the job site, I give you what, $1 million building me a house. They say, hell no, I'm not gonna sign for that. What we need? What do we need? Say it again. Concrete type. So F prime C, say for KSI. What else? You don't ask, I don't tell. Then you're in trouble. Ask me, what do you need? Strength requirement, what is that? M, U or N? U or N? Think again. M, U. Factored moment. Close. Very good. Factor moment. All right? Okay. I'll tell you that, but wait a minute. What else I need? You're designing it. You're building it, okay? You're building the project. What do you need? We got a concrete, right? What else? Frozen. This is what? Reinforced concrete design. You got a concrete. What else? Steel, right? What do you need for steel? Grade, right? Grade 60. There you go. Okay. What else? What else do you need? What else do you need? And that is all. This is pretty much it. Okay. All right. So you see, you need this information, right, to start your design. All right. Now, what about MU? How do we determine MU? Let me tell you how do we determine MU. So I am putting this beam in a singularly supported fashion on a MODA I-94 bridge nearby Winsburg. We're nearby Winsburg. Okay. I'm telling you that I have a dead load on top of it, and I have a live load on top of it. So to tell you, this is omega U equal to what? 1.2 that plus what? There you go. Well trained. There you go. You know it. 1.2 that, 1.6 live. Okay. So now you know it. And I say, look, you guys are pretty smart. I'm not going to play games about it. I say, look, I'm just going to tell you. The moment diagram look like a parabolic, right? And it's the maximum moment at the middle of it, right? And let's just say that the span length of the beam is L. And mu, of course, in the middle span right here, and equal to what? Mechanics, material, static, 1/8 L squared multiplied by what? Omega U, right? Omega U. Okay. All right. Now, let me ask you a question. Say if I have omega dat equal to a 1.5 kip per foot, omega L equal to 2 kip per foot, what an L span length is say 25 feet. What will be my MU? Come on, let's do it. What will be my MU? So MU equal to 1/8 L squared 25 feet squared multiplied by omega U, and that is 1.2 multiplied by 1.5 kip per foot plus 1.6 multiplied by 2 kip per foot. Is that right? So what do I have? Help me. I'm not that smart, okay? I cannot do hand here now, too much. What do you have? Come on. 390.6 cubic foot. Do I get a second? Can we move on? Is this good? Anyone? You also good. Okay. So say this is what we get, right? This is what we get. Okay. Now with this, I'm going to ask you to design the section for it. So where do we start? You have MU now, right? So I'm going to start my design process. Design. And how do I design it? How do I start? Calculate phi, right? How do I calculate phi? From where? Phi mn. Phi mn equal to, I know, phi mn equal to what? Bigger or smaller than mu? Sure, before we go there, phi mn bigger or smaller than mu? Smaller than mu? Oh boy, we're in trouble, right? The design has to exceed the required, right? So phi mn has to be bigger than mu. Okay, but should we start with phi? Why do we start with phi? Say again. We know beta 1. How do we know beta 1? That's right. So beta 1 is what here specifically? 0.85, right? And what else? What else? What else? Anybody? Anyone? Actually, I would say I don't know where to start. Too many leads, right? It's in the crime scene. Too many suspects. I have phi, I have mn, I have beta 1, you know, I have A, I have B, I have everything, right? Where do we start? Okay, where do we start? Now, what do we want? What do we want? Design for what? Design for what? Specific strengths and design for what? Come on, read it out. Unknown reinforcement, right? Now there are two information about reinforcement. Gradation of the reinforcement. What is the grade for reinforcement? Grade 60. What else? Bar size. How many bars? That is what? A, S. I'm not going to give you for free. I need you to think. Okay, because you think, you remember, you understand, and you will never forget. So simplify. What we're looking for here is simply the area of steel. Okay, AS. That's what we're solving here, right? Then things become clear. Why is that? Because what is the equation for Mn? Remember, Mn equal to what? T, tension, right? What is tension? AS, what? Fy, yes. And then bracket inside ds minus what? A over 2. Remember this equation, right? What did we say about ds? For one layer of bars assumed, one layer of bars, what is ds? H minus concrete cover. What is the concrete cover here? 2.5 inch. So we know, isn't it? We know, isn't it? Right? So now what is unknown here? That is what? That is what? A is unknown here. Is that right? A is unknown here. So I look at this equation and I say, look, how about let's just assume the A. Can I do that? First, and then go find about how much how much reinforcement area I have. I have reinforcement area, I have total tension. I go back to balance the compression, then to confirm A. So I start from A, resides back in A. So that is my thought process. So that's how I start. Okay. So with this, I can now finally start. So let's just keep a bracket here, and this is digress, and this is thought. Okay, and let's start doing it. So with this, I start to say, look, from this equation, drag it down, and then say AS, right? And Fy ds minus half A, that equal to Mn, and that multiplied by phi has to be greater than or equal to Mu, right? So AS has to be greater than equal to Mu divided by phi Fy ds minus half A. So that's how I'm going to start. Okay, this is very important. You need to understand why we're starting here. Okay, so that's how I'm going to start. So with this, I'm going to start, right? Looking back on the right-hand side of the equation, do I know MU? I know, right? Just calculate it. What is it? 300 something, isn't it? What is 300? 390, right? Let's just pick a round number. So 391 kip foot. Okay. Do I know feet? Do I know feet at this point? I don't. Why I don't? Because I don't know A, right? If I don't know A, I don't know C. I don't know C, I can now calculate the strain of steel. I don't have the strain of steel. I can now use that equation to get my feet, right? But I need it. I desperately need it. When you need something and you don't have it, what you do in civil engineering, you assume. You assume. You make it up. Okay? No shame in that. Make it up first. You will come back confirm that though, but you make it up so you can get going, right? You cannot get stuck, right? So what will you do to make assumption for phi? What number you pick? Assume the tension control, right? Because that's in our favor. What is that number? Tension control phi equal to what? 0.9. You said it, right? So 0.9. Okay. Keep in mind, this is assumed. You borrowed from the bank, you assume something, go back, have to pay the debt. Okay, later we'll have to confirm that, but that's where we start. Assume that. Then what is the gradation of steel? 60 KSI. And now, what is ds minus half A? What is ds minus half A? Do I even know that? Do I even know that? I don't. Isn't it? I said we have to assume that. How do we assume that? We assume this fellow right here equal to 0.9% of ds. Okay. Approximately equal to 0.9% of ds. So with that assumption, I say, okay, this is, let's just assume is a 0.9 multiplied by ds. What is ds? H, what is the height of it? What is the height of section? Somebody remember? 24. 24 minus what? 2.5. There you go. Help me out here, please. So that is how I'm going to do that. Can I go straight into calculation right now? I can't. There's a unit mismatch. Top, what I have, kips, foot. Bottom, what I have, kips, inch, right? So I need to convert everything back to inch. So multiply 12 inch per foot to convert it. Now everything's in terms of KSI inch or kips inch, right? Now, please help me out. Do this calculation. What you end up with? What is this number right here? Come on, do it. You don't find it in the notes, okay? Notes is something totally different. Okay, I had it totally different in the notes. Okay, come on, help me out here. Help me out. 390. It's pretty big. 12 inch per foot, 0.9, 60 KSI, so on, so blah blah. What do you have? 4 point what?
4.49 inch.
4.49 inch squared. Second, good. So let's say roughly 4.5 inch squared. Bless you. So given this number, how many bars? Let's say number 9 bar, okay? I want number 9. Bob, simple-minded, pretty simple guy here. Number 9 bars only. How many bars I need to cover this? 5. What is beam width here? B, 12, right? Question, can I fit number 5 bars, number 9 bars into this width? Can I do that? I don't know, isn't it? I don't know. I got to run the detailed calculation, remember? And that's going to take forever, right? So we take the shortcut. What is the shortcut? Table A5. There you go. Table A5. So let's take a look, right? Table A5. So I go back to table A5. Where is it? Here. And I look, right? Help me out. 5, number 9 bars. What is the minimum beam width? 14.5 inch. What does it mean? Means that I cannot design this section to resist this 391 kip foot with number 9 bars. I have to either increase my bar size or I have to increase my section, isn't it? I increase my section. So that's a check already. That's a check already. Do you see that? Okay, wonderful. All right. But Bob is lazy and I want to finish this lecture in reasonable time, okay? So I'm just gonna say, let's keep playing along and reduce the MU here. Okay, I'm not going to design a section for this capacity too big. Okay, let's play a safer game. Let's say Bob say, okay, start all over. And now you can look at old lecture notes, right? Start over. Let's say mu equal to 145 cubic foot. Very small number. Why is that? Because I'm lazy. I want to keep using 12-inch by 24-inch of a section. I want to keep use number 9 bars. Okay. I'll show you later how we can design for a higher capacity. But today, let's go with small capacity first. Okay. I just want to show you there's a pre-check. Okay. There's a pre-check. You know right away whether this design will work or not. Okay. So take you only 5 minutes on the job site. You know immediately whether this section of size is this big enough for your beam or not. Get it? Right? So don't rush into it, right? Go there, do a quick check. So you know immediately, okay, can this section work or not? All right, so apparently it doesn't work. So I'm gonna reduce my load, okay? And give you an easier problem. I say mu equal to this much, and let's recompute. So now AS, forget about it, right? Drink your beer and forget about it, right? Say AS equal to 145 cubic foot multiplied by 12-inch per foot, converting the cubes inch, and then come back here, 0.96 KSI, and 0.9, a 21.5 inch of depth. Okay, you run this number. I'm going to speed up since this is repeating. So this has to be 1.67 inch squared. Okay, 1.67 inch squared. Now you look at this number, 1.67 inch squared. I have I want to use number 9 bars. How many bars I need to cover this? 2. Can my 12-inch beam width accommodate 2 bars? Easily, right? So easy peasy, no problem, right? So I'm happy, right? But can you go like this? Can you put two number 9 bars and just go in like this? Can you do that? No. What do I owe? What did I owe? What did I make assumption? What kind of assumption I made to begin with? First assumption, phi, is that right? Second assumption, A, right? A, how do I make assumption A? 0.9 ds, remember that? So I need to check these two, right? Don't forget you owe your debt. You had to pay your debt, right? So second step, I need to go back and check my A. So what is A? I start use compression equal to tension. So 0.85 F prime C AB equal to AS FY. Okay, without providing any bar yet, I'm just gonna say A equal to AS FY divided by 0.85 F prime C and B. So AS 1.67 inch squared. Is that right? Yeah. And multiplied by 60 KSI divided by A 0.85 multiplied by 4 KSI and multiplied by 12 inch of beam width. You do the calculation, you end up A of 2.46 inch. And that is your effective compressive zone. So with that, you have your C equal to A over beta 1 equal to something. But can I continue like this? Not yet. Why is that? I need to do one more thing. Because now I got A, I need to do ds minus half A to see what is my JD here, right? So now AS, recalculate my reinforcement, need to be greater than mu divided by 0.9, which is phi Fy. And now I know my depth minus half A because A is known. Okay, so first step, I need to confirm this, right? So this is 145 cubic foot multiplied by 12 inch per foot divided by A phi, still 0.9, 60 KSI multiplied by ds, which is 21.5 inch minus A now calculated 2.46 inch divided by 2. And with this, my AS has changed to 1.59 inch squared. Okay. So what did we do? We guessed the AS. Okay. Use that AS, go back to check A. Use that A to go back to check AS again. Okay. So iterations 1. So we finalize AS now. And at this point, we say, now you can select bars. Okay. So how to select the bars? 1.59 inch square, right? 1.59 inch square, right? Can I do this? Sure, you can do that. So I have option now, isn't I have option now. I can do number 9 bars, right? Remember number 9 bars. And 2 number 9 bars gives me an AS of what? 2 inch squared. That covers that 1.59 inch squared of requirement. But I can also option for number 8 bars. But to do number 8 bars, how many bars do I need? How many bars do I need? 2 or 3? 2, I end up with 1.58, just a hair less, right? So I need 3 number 8 bars. So what is the cross-section area for number 8 bars? 0.79 inches. So 3 number 8 bars, how much? 0.79 multiplied by 3. Come on, what do you have? 2.37 inch squared. Do I get the same? And that is, yeah, well, that is bigger than 1.59 inch squared. So I either go with 2 number 9 or 3 number 8. What will you choose?
Less cost.
Less cost, fine. So let's say 2 number 9 bar, 3 number 8 bar, not much differences. So which way you go? Where you go? In the whole world of reinforced concrete design, remember the first lecture, chapter 0, right? We talk about the cost. That's the right angle. But when we talk about cost, there are 2 parts of cost: materials and what? Labor, right? So which way is more expensive? Materials or labor? Labor. So now, how much labor it takes you to put 2 number 9? How much labor it takes you to put 3 number 8s? Which one's less? 2 number 9 bars. So we go with 2 number 9 bars. You got to think, folks. You got to think, right? You got to think. You say, but this is only 1 bar difference. We're talking about 1,000 beams in design office, right? Each beam will cost you 1 bar. How many bars it costs you every day? Okay, so think of it. We're talking about civil engineer bulk volume, right? So I will go with 2 number 9 bars because it's cheaper. And also just to sweeten the deal up, right? Sweeten the deal up. This is 2 inch square. This is 2.737 inch square. I get less steel anyway, right? I use less steel anyway, right? So go back to material. This is even better. This is even better. So lock and load. 2 number 9 bars is my option. Okay, I'm gonna go with that. All right. So what to do next? Well, what to do next is that I have a section. It has a width of 12 inch and a height of 24 inch and a depth of 21.5 inch. And I opt for 2 number 9 bars here, okay, at the bottom here. And I know that my MU equal to 145 kept foot. Okay, that's what we know right now, right? That's what we know right now, right? So what do I need to know? I need to check Feynman has to be greater or equal to MU. So this has just turned into an analysis problem, isn't it? Analysis problem you have seen, you have competed, and you will be doing homework about. Is that right? We have covered it. So today, this is our first quiz, take home quiz. Finish the lyric. Oh, sorry, finish the rest of the problem, right? Finish the rest of the problem, okay? Quiz number 1. Okay, check this section. Okay, and show me that Feynman greater than equal to MU. Clear? Clear? All right, so what is design for unknown reinforcement? Is all this hoopla, 1, 2, 3, 4 steps that added on to analysis. Basically, right at the step that pick bars, right? Once you pick your bar, it go back to analysis. Just verify that. Okay. All right, I'll upload the quiz 1 and you will do it, and hopefully before next lecture, which is Wednesday. We are not going to meet Thursday this week, okay? It's going to be a pretty short and sweet week this week. Okay. All right, I see you on Wednesday. Okay. I'm sorry. Oh, sorry. Yeah, go ahead. Can you see it? Yeah. Any question? Approach me and I'll help you. Okay. If not, I see you on Wednesday. Thank you very much. Oh, I forgot about that. Career First Wednesday. I will do recording. How about that? Yeah.